Hello, ladies and gentlemen. It is my pleasure to present Dr. Fazan Kazami's research project at InterPore 2022 Annual Meeting. Dr. Kazami's expertise is in fluid mechanics and he is also an assistant professor at San Jose State University. My name is Mingjia Shu and I also go by Chris. I'm a graduate mechanical engineering student at San Jose State University. Jason Wong is a former undergraduate mechanical engineering student at San Jose State University, and now an undergraduate mechanical engineering student at University of California, Los Angeles. Jason and I are the student assistants for this research project. The topic of this research project is 2D particle tracking velocimetry for flow in porous media. Flow in porous media is ubiquitous in many engineering and natural systems, many of which occur in the geosphere and they are intimately linked to energy, environment, and water resources. Transport phenomena in the porous domain is closely linked to the pore scale velocity structures. Thus, an important ingredient in development of transport models is having reliable pore scale experimental velocity data. Presence of a second immiscible fluid phase in the porous medium can profoundly impact flow and transport phenomena. In this work, we present results from 2D particle tracking velocimetry experience of single-phase flow in 2D microfabricated porous media, also known as micromodels. The method of stitching broken trajectories is introduced. Lagrangian particle trajectories in the continuous flowing phase are obtained, and the velocity and acceleration statistics are presented. A 2D silicon micromodel with heterogeneous structure inspired by sandstone was manufactured in the microfabrication lab at San Jose State University. It has a porosity of 50.8% and a minimum flow size of 12 micrometers. The SEM images of the test section of the micromodel under a microscope is shown in Figure 1. Figure 2 shows the side view and top view of the micromodel. The water flow, which is dyed with 1 micrometer fluorescent tracer particles, thermal fissure F8819, enters from the left edge and exits on the right edge under room pressure and temperature. The flow rate is controlled to be 0.001 milliliter per minute by the syringe in pulling mode at the outlet. The green section is the area captured by the microscope and the cameras. Images are taken at 30 Hz with 0.65 micrometers per pixel magnification. Figure 3 in the lower left corner shows the experimental apparatus, and Figure 4 on the right shows the optical imaging system setup. Images taken from the experiment are preprocessed using an image processing software called ImageJ to even out some bright area of the images. Then, the preprocessed images are imported to an open-source particle tracking software called OpenPTV to get particle trajectories across 300 images by tracking the dye particles. Due to the image quality and the limitation of the OpenPTV, it is necessary to stitch the output trajectories from OpenPTV, since a lot of particles are lost track during the process. We developed a broken trajectory stitching method based on the work by Su 2008, which is shown in Figure 5. The red solid curve represents terminating trajectories, and the dashed line represents its predicted travel area based on its velocity recorded from OpenPTV on the second to the last frame and the search radius. A search radius is defined, and the predicted particle location is used as the search center. The green, blue, and yellow curves represent 3 future trajectories. Only the starting point of future trajectories within the search radius will be considered. Search radius will increase as the search frame gap increases. Theta tail is defined as the angle of the last segment of the terminating trajectory. Theta length is defined as the angle between the starting point of the future trajectory and the search center. Theta hat is defined as the angle of third segment of the future trajectory. Deviation angle is defined using the formula shown on the right side of Figure 5. The future trajectory of the smallest deviation angle will be chosen to stitch with the terminating trajectory. The broken trajectory stitching process is performed using two programming languages, Python and MATLAB. Figure 6 shows the repair particle trajectories where the blue curves are the original particle trajectories from OpenPTV and the red curve are the new created lengths used to stitch the broken trajectories. A local zoom-in view is also displayed on the right of Figure 6 for better visualization of how the broken trajectories are stitched together. With the repair particle trajectories, we can plot and analyze the flow statistics. The spreading of fluid particles shown in Figure 7 is categorized by the root mean square displacement in the longitudinal direction sigma x and the transverse direction sigma y. Both root mean square displacement profiles in the x and y directions display the change of the spread of the particles relative to the initial position. The initial length of the x direction root mean square displacement is super diffusive at early time t to the power of 1.2, but during the second half of the length, the flow enters Fichtean dispersion based on how well it fits the Fichtean scaling, which is the square root of t. The formula used to calculate sigma is shown on the right. Correlation length lambda is a quarter of the pore size. Figure 8 shows the probability density function of the longitudinal Lagrangian velocity increments normalized with respect to the standard deviation of increments with 1-time lag, 2-time lags, 3-time lags, and 5-time lags. We can see the probability density function has a narrow peak at 0, with exponential tails for all time lags and follows the trend of Gaussian distribution. The formula used to calculate delta V is shown on the right. Acceleration autocorrelation and velocity autocorrelation with respect to normalized time are plotted in Figure 9 and 10. Time is rescaled with respect to TA to be the normalized time, where TA is defined by the pore size of the micromodel divided by the velocimetry flow rate. To quantify the correlation and statistics of Lagrangian acceleration, Lagrangian velocity increment associated to time lag tau, which is shown on the right-hand side of Figure 9, is used. The formula of acceleration autocorrelation is shown below. In the case of acceleration autocorrelation, the autocorrelation coefficient sharply declines to near zero values, suggesting dissimilar acceleration throughout. In the case of velocity autocorrelation, as shown in Figure 10, the autocorrelation coefficient decreases exponentially with normalized time, which matches the pattern seen in Figure 9. The formula used to capture velocity autocorrelation is shown on the right-hand side of Figure 10. It is important to note that Figure 9 and 10 show chaotic behavior at the tail section of the plot. This is probably due to an understitching of longer trajectories. In conclusion, at the current stage of the research project, the length of particle trajectories is increased and the number of particles is reduced due to the stitching of broken trajectories. However, the linear connection method becomes less accurate as the search radius increases with the frame gap. Also, there are still a lot of short trajectories after stitching. Therefore, a more accurate stitching method, such as the least squares approximation, needs to be considered. Particle tracking velocimetry was carried out for single-phase flow in a micromodel. Data processing pipeline has been set up to extract Lagrangian statistics from PTV data. This is an ongoing research project, so the next step is studying multi-phase flow to determine the similarities and differences compared with the single-phase flow. The authors Acknowledge support from the National Science Foundation, award number 19533352, and the San Jose State University. Thank you for your time. I hope you enjoy our presentation.